So now we're going to talk about what are called vertical asymptotes. We kind of have alluded to this before, but let's say you have a graph, and there's a vertical asymptote at A. Well, what that means is something's going to happen with your function. Maybe it's going to approach the vertical asymptote like that. If that's the case, then you can say as x approaches A from the right, then f of x is approaching infinity. Okay, so that's one case. Now, what if you have a vertical asymptote at A, but it's like this, and it does this kind of thing? Then you could say, as x approaches A from the left, f of x approaches infinity. But you could have a vertical asymptote, and maybe it goes like this. Maybe the function goes like that. Then you would say, as x approaches A from the right, f of x approaches negative infinity. Okay, so that would be that one right there, right? Because it's from the right, you're going, you're moving toward the A, and it's going down, right? Okay. And then our last case, you have a vertical asymptote, and it's doing something like that. So as x approaches A from the left, f of x approaches negative infinity. Okay. So those are the cases you would have. It's going to either be getting very large as it approaches the asymptote or very small as it approaches the asymptote. Okay, so how do we find vertical asymptotes? So we had a function a while back, a few videos ago. I don't remember what the numerator was, but the denominator was something like this. And we said, oh, you can't have 0. X can't be 0, it can't be 2, and it can't be -5. So we said the domain, well, we said the domain was from negative infinity to -5, and then -5 to 0, and then 0 to negative or to 2, and then 2 to infinity. Okay, well, I don't know why I wrote the domain out, but this is all we really need to know. It means there's going to be a vertical asymptote there'll be one at 0, there'll be one at 2, and there'll be one at -5. So the zeros are where of the denominator, that's where your vertical asymptotes are. So for vertical asymptotes, VA, maybe I should say vertical asymptotes. Well, anyway, you know what I mean, vertical asymptotes. To find those, in our function, when we have P of X over Q of X, you're going to have vertical asymptotes at the zeros of Q of X. So you find the zeros of the denominator, that's where your vertical asymptotes are. So it's probably easier to say it that way. There's one little thing I have to mention though. There are no common factors of P of X and Q of X. So we talked about those situations where something might cancel. And if that's a different situation. We're not ready to talk about that yet. Okay. So it says find vertical asymptotes, if any. You don't have to have vertical asymptotes of the graph of each rational function. So you look at the denominator. You say, what can x be? What are the zeros? X, well, let's say it this way. The zeros are -3 and 3. So you have vertical asymptotes at -3 and 3. We would write that as x equals -3. That's one, because it's a vertical line. That's one vertical asymptote. And x equals 3. Those are the two. In this case, you get two vertical asymptotes. You can have lots of vertical asymptotes, or you might not have any. Okay. Now, here's the situation. You know that you can't have the zeros are 3, -3, and 3. But when you factor that, x plus 3 over x plus 3, x minus 3, you see that those factors cancel. And what that means is you won't have a vertical asymptote at negative 3. You'll only have a vertical asymptote at 3. So you will have a vertical asymptote. I gotta have a way to abbreviate this. Vertical asymptote at 3, or x equals 3. That'll be your vertical asymptote. You won't have one at negative 3. What happens is you get a hole in your graph at negative 3. We'll talk about that later when we start graphing them. Okay, now we have this denominator. And remember when we had it before, x squared plus 9? That's never going to equal 0. So there are no vertical asymptotes here. No vertical asymptotes.